In this video, we are going to explain our experiment in gaining further insight on the impact of agricultural practices on water quality and its real-world importance. The experiment offers a compelling glimpse into how advanced laboratory studies can contribute to enhancing water quality, particularly in the context of agricultural practices. The relevance and importance of such studies are profound, given the substantial impact of agricultural activities on water bodies. Next, we will discuss several real-world applications and the significance of the experiment in understanding and improving the intersection of agriculture and water qualities. First, a red dye solution was made to create a calibrated curve. To do so, we utilized 20 milliliter of water into 5 containers, and then put the red dye dilution of 10 milligram per liter, 20 milligram per liter, and 30 milligram per liter, 40 milligram per liter, and 50 milligram per liter. We then place these solutions into the corvettes along the blank into the spectrometer at 504 wavelengths, which is the optimized wavelengths for the spectrometer for the red dye 40. The reading we obtain and the subsequent calibration curve is shown on the graph. Next, a sample of mulch was collected from outside of Snihao. For the experiment, 2 groups were created. The first group was mulch that weighted out to be 9.007 grams, and the second group was GAC that weighted out to be 9.001 gram. Then we obtained 2 containers for 16 millimeter red dye with 15 milligram per liter concentration. The mulch was torn up into smaller pieces to about 0.5 inches strands to mitigate potential clogging, and the mulch and GAC groups were put into the red dye containers. The contents were placed on shaker at 170 RPM for 48 hours. For the column portion of the experiment, we used 2 columns for the respective groups, 17 diameter tubing, same inlet and the same speeding of both groups. The sand utilized in the columns is also the same weight, out to be 89.0325 grams and 89.0524 grams. The columns were filled with the sand GAC mixture and the sand mulch mixture. We stopped the pump flow rate to 20 RPM and timed out the flow rate ourselves, determining that the actual flow rate was 16 milliliter per minute. Red dye was then pumped, and the time was recorded for the moment the dye reached to the top of the column until it went through the column and right at the bottom. Both columns were recorded at their respective time 0. Then every 15 minutes, a sample of the dye that had gone through the column was collected into a corvette. We left in the system running overnight, lowering the pump setting from the 20 RPM to 4 RPM to allow for enough influent to last, and collect 2 more samples for each at 9 a.m., 12 p.m., and 3 p.m. the next day. Although we are still analyzing and processing our data, we were able to see how slow increase in volumes over time due to our slow flow rate and limited influent red dye. The result of GAC column and mulch column are shown. We recognize that our breakthrough time was likely within the first 2 hours and needed more frequent testing with the earlier times to see data before and after breakthrough. My bad.
I'll read this one and then, no, you're good. I'll cut this one too. Okay. Next, we'll go into the relevance of our experiment and real-world applications with agricultural practices with regard to water quality. So the experiments focus on the breakthrough characteristics of red dye 40, which is a proxy for various agricultural pollutants like pesticides, helps us understand how contaminants from agricultural runoff behave in water treatment systems. Activated carbon and coagulant nanoparticles are common in industrial and municipal water treatment processes, and their effectiveness against agricultural pollutants is crucial for ensuring safe water for human consumption and ecological health. Next, agricultural runoff often contains a variety of contaminants, including pesticides, herbicides, and nutrients such as nitrogen and phosphorus, which can degrade water quality. By studying the adsorption capabilities of materials like activated carbon and nanoparticles, this research can lead to better strategies for managing these contaminants at their source or during their transit in waterways. For example, enhanced filtration systems could be designed based on the data obtained from such experiments to be installed at critical runoff points. The insights gained from the experiment regarding the efficiency of adsorption processes can directly influence the development of more efficient and cost-effective water treatment technologies. These technologies can be particularly useful in agricultural areas where water recycling and reuse could significantly reduce the demand on freshwater resources and mitigate pollution. Data on the adsorption efficiency and characteristics of different materials in removing specific contaminants can inform policymakers and regulatory bodies. This can lead to the formulation of more precise regulations regarding allowable limits of various pollutants in runoff water and the adoption of specific best management practices, or BMPs, in agriculture to prevent water quality degradation. The application of such advanced treatment technologies and the understanding of contaminant behavior facilitate more sustainable agricultural practices. Farmers and agriculture managers can use this information to choose less harmful chemicals or adopt practices that minimize the impact on water quality, contributing to overall environmental sustainability. Finally, such experiments can help in educational efforts, raising awareness among agricultural professionals, environmental scientists, and the general public about the impacts of agriculture on water quality and the technologies available to mitigate these impacts. This can drive more informed decision-making at all levels, from individual farmers to national policy. So in summary, the laboratory experiment performed is not only about understanding the specific adsorption characteristics of a dye on activated carbon or nanoparticles, but it's also about leveraging scientific insight to tackle real-world problems like water pollution from agriculture. By translating these laboratory findings into practical applications, significant improvements in water quality and agricultural sustainability can be achieved. This highlights the importance of continuing research and development in the field of environmental science and engineering. Thank you. Okay, I think that's good. I'm gonna
How long is that, Coach?